Okay.
No, because you're ready. Oh, right.
Okay. We're gonna get started with the embedded code now. We'll be referencing some stuff in the slides, so you can go to the meetings link to get that information if you want to follow along.
It might not be updated immediately, but in 5 minutes it should be there on the website.
So to discuss PWN generally, yesterday was PWN 1, so you might have already seen this already, but in general, it's binary exploitation, which are exploits that abuse the mechanisms behind how compile code is executed and deals with what the CPU actually sees or executes on or near the hardware level. And so most modern exploits tend to fall into this category. For PWN in embedded context, it deals with lightweight OS like RTOS, Zapper, rather than the full-featured OS of like typical computer systems. The attacks are still very similar to regular PWN, but they deal with different memory layouts and architectures. And so it will also involve utilizing the communication protocols such as like UART, SPI, I2C to get the firmware dumps of the device that we're attacking.
So yeah, we'll just be going over the general layout of memory for embedded systems in general. So you can refer to this diagram just to know the different sections of memory that we have. Obviously, this diagram isn't comprehensive to all sorts of microcontrollers and embedded systems, but we just want to highlight what the differences are between embedded system memory and regular computer memory. So the main differences we're going to have are our embedded system has flash memory, EEPROM, and SRAM. And in general, we kind of just have a chart here to show you guys the analogs between computer memory and embedded system memory. So for volatile memory, we know that computers generally use DRAM, but our embedded systems are going to use SRAM. For non-volatile and persistent storage, computers tend to use a separate hard disk drive or SSD, but our embedded systems are going to use flash memory and EEPROM. And EEPROM, for those of you who don't know, is electrically erasable programmable read-only memory. Bootloaders for computers are going to be BIOS or UEFI, but for our embedded systems, we're going to use ROM or flash directly.
So in order to evaluate embedded programs, there are two different protocols to debug the microcontroller. So we have JTAG, which is a low-level communication protocol for debugging or programming the MCU. So it has four different signals. TDI or TDO, which allows you to send the data in or out of the chip. TCK to basically see the clock for data. TMS, which allows you to direct the state of the chip. And ICSP is an alternative for other MCU architectures. So due to the power of JTAG to allow you to directly debug the code, in order to limit the sort of control you can have over an embedded system, many manufacturers will implement total or partial JTAG locks, which will limit the debugging memory access of the JTAG interface. Even despite these locks, depending on the system, it's still possible to attack the bootloader directly. Or if you're not allowed to read flash memory, there might be existing gadgets in the code that let you read the flash memory anyways. Or if there's a block on reading flash memory altogether, it might be possible to repeatedly restart the device so that you can just slowly extract individual words from flash. And even if that's not available, you can read the SRAM memory to still get program information. So even on embedded systems, the complexity of the CPU makes it possible to find corner cases that you can easily exploit like this.
Good question. If the manufacturers are just going to lock the JTAG, why not just not include it in like the production version of the device?
I believe JTAG is during the manufacturing, they'll use that to sort of test their product. And then if they're releasing it for production, you'll usually see a total JTAG lock, which will pretty much disable you. It will only give you like, I think the bypass register, which provides essentially no information. But even with that block, like you can still attack the bootloader from there. So it pretty much depends. Like all of these corner cases are more like they don't intend for you to read it, but even with that, you can still make those attacks.
No, I mean, like, why not just remove it?
So I think one bit of that is that it's might increase costs for manufacturing because now you have two different versions of the chip, one with JTAG, one without. I think that might be a reason. A lot of chips, they'll also talk about it, but a lot of chips will also have like this, which people disable JTAG. One reason why people might keep around JTAG is because sometimes if chips break, you can't send them back to the manufacturer for repair, and they need access to that or to debug. Although usually you shouldn't use JTAG for that.
Why not?
Well, preferably you have your own system,
Oh.
like a software level thing, which would do like print out debug information.
Yeah, also sometimes manufacturers do allow like partial JTAG access so that consumers can actually modify it or like fix it on their own without having to go through process like sending it back to the manufacturer.
Right, so now we're gonna look at some case studies of different types of attacks. Obviously, there's so many different microcontrollers in the world, and people have figured out many exploits for all of them. And all the exploits are very specific to each type of microcontroller. So we've picked 3 examples from the book by Travis Goodspeed called Microcontroller Exploits. Highly recommend if any of you are interested in just like learning about different types of microcontroller exploits. He talks about attacking Ataris, Tamagotchis, Game Boys, all sorts of different things. So highly recommend this read. So the first case study we're going to go over is a buffer overflow that deals with a Dish Network smart card. The second one is SPI bus sniffing. So basically how we can use an SPI bus to read a firmware image or dump a firmware image directly. And then also how we can use UART access to also read a firmware image. Okay, so for our first case, the buffer overflow, basically the chip that was used had or the memory layout of the chip that was used had an SRAM ghosting property. So ghosting is basically when we copy writes to duplicated chunks of memory. So we'll have a slide after that kind of breaks down the different memory layouts, but we're in this case focusing on the property of SRAM being ghosted. So basically what this means is that a write to address 0220 is the same as a write to address 0020 and 0420. So the SRAM here, basically a write to any of these ghosts also gets copied over to SRAM, and that sounds like a very vulnerable thing, like property of the memory. So we weren't sure why exactly this smart card had that property in general, but the book kind of goes over how this property is very easily exploitable. So basically what we do is, you see this buffer here, we overflow this buffer onto the ghost section, and so any part of the buffer that gets overflowed onto the ghost section also automatically gets written to this SRAM and to this ghost. So then if we want to just modify the SRAM, we can just overflow this buffer and then write into the ghost. And then that write automatically gets copied into this part of the SRAM. And then we can basically just corrupt any actual part of SRAM that we couldn't write to before.
Okay, for the SPI bus sniffing, this is for a USB update protocol. So JTAG lets us write an application into the unused SRAM of this USB protocol. And so this program, what we want this program to do is just transmit the packets of flash memory via the SPI bus. And so because this is like a USB update protocol, the bootloader is very controlled, but it allows you to set the address pointer of the program that you're executing. So you just set the address pointer to the application that you write, and then when you exit the bootloader, the execution is just going to run that program, and so you're going to be able to extract the firmware via the SPI. And yeah, so just depending the package you read from the SPI bus gives you the firmware image. And then for another example of just reading from the communication protocol, we have the HID RW400 card reader. So like for credit cards, this is like the same chip you use in the card reader. So every memory page in the chip has these 3 protection bits: code protection bits, write protection bits, and table read protection bits. And so the bits are clear to enable the protection. And in order to set the bits, you have to erase the page. So if you want to change the protection on a page, you have to remove its data basically. Yeah, and so this engineer Mariak notices that the CP and WO the write bits are cleared, but the EBT bits aren't. And oh yeah, I'll say for the table read protection bits, it allows you to run code on a page. So does anybody have any ideas why the EBT bits aren't cleared?
Doesn't allow, like, there might be a memory page you can access it right into, but it's in order to prevent overrunning stuff on the machine, and they don't want to run the ADT that's are set to presumably it's zero, or just like not down the line.
So okay, well, what this means is that the code protections and write bits are cleared, meaning that you're not able to read or write the memory page. But then the EBT bits are, so you're actually able to run code on the memory page.
So when you clear the whole page, and you just.
So clear just means like so the default state for each bit is going to be like all ones, and so cleared basically signifies that that they're enabled.
Sure, but
Yeah.
you write and then clear the bits and then runs.
If you want to set the bits, you would have to erase the page. So if you were, if you were to do that, you wouldn't be able to keep it.
You can use also next to be good.
Yes, exactly. If all three bits were clear, then you wouldn't be able to run anything, which would make the whole device pretty useless. The problem is the EBT bit, since it allows you to run code, it allows the entire firmware to be dumped by shellcode running on a page. So our exploit is to erase some random page, and which allows us to then disable the protections on that, and then we can write shellcode to dump the firmware through UART. So this causes us to lose the information on that page. But since that's only one of many memory pages, we're able to get all the information from everything else. So, and then the shellcode is written by bit banging the ICSP through the FDI chip GPI functions. Yeah, so this is just part of the like the chip design. It just in order to prevent people from like reading like say you don't want somebody to read the information on a page. If they're able to just set the right like the CP bit to off, right? So like they disable the CP pin, then you're able to read the page when that's not intended. So in order to basically just say like so yeah, the manufacturer will send all these pages with the code and write bits cleared so that you like attackers can access that information. And then if you want to change that information, then you have to erase the page. Yeah.
What is the ICSP that you mentioned?
Yeah, it's basically an alternative to JTAG on some architectures. It does the same thing. It allows you to communicate, like debug and program the interface. Yeah.
So, for the exploit, you have to erase one page, disable all protection, so you can read, write, and execute there. You use a debug to write the ICSP to write some shellcode, and then you run that shellcode.
Yes.
So the shellcode needs to dump firmware from the other pages.
Yes.
So how is it able to read those other pages if the code protection of it is off? Or is weird, so you won't be able to read.
Right. The code protection bit means that that page can't be read, but then other pages would be able to read. Like if like you erase this page and then disable all the protection, so then you're able to read, write, and execute on it. So other pages, all the other pages have execute permissions. So even though you're not able to read them directly, you can run the code that you have on this page to then dump all the firmware.
So basically what we're doing is we're just we're clearing all the permissions that we have all of them for one page. Then we're writing our own code onto that page, and then that code can execute any other page.
Yes.
Okay.
And then there's something else where if you want to like not lose that page, you can use another chip and connect it. That was more complicated, but yeah.
So now we'll talk about the different types of defenses and protections that we get specifically in an embedded context. So a lot of MCUs have privilege levels. The most commonly known one is ARM. So most MCUs have two privilege modes, generally one privileged mode and one unprivileged mode. And ARM has a handler mode and then a thread mode that you can change to either privileged or unprivileged. And that is one form of memory protection because most MCUs also hopefully have an MPU and memory protection unit, which is similar to an MMU that most computers have, or all computers have. And this enforces privilege levels on different regions of memory. So you don't want unprivileged or something in unprivileged mode or a user program in unprivileged mode to be able to access secure regions of memory. So that's what an MPU does. It kind of enforces each of these privilege levels on different regions of memory, and it does this by raising memory management faults when violations occur. And another way protection or memory is protected is through bus level protection. So when we have peripherals that are that we interact with using SPI or other communication protocols, there's usually like a master and a slave. So we have like the master signal and the slave signal coming from the peripheral. So if we have a device that we're interfacing with, we can have a bus level protection such that we label masters as secure or unsecure or insecure, sorry. And these masters can based on whether a master is secure or insecure, we can decide which regions of memory it's going to access and only allow it to modify or read or write to specific regions of memory based on its privilege level. So we can assign privilege levels to masters and slaves as well. And this is one example of this is ARM Trust Zone M. So if you guys want to ever look into that, that's one of the main examples. So now we wanted to discuss potential exploits on our MCU that we'll be using for eCTF in the 2026, so next semester. And our chip that we're using is the M0 Cortex. So we've linked the data sheet in the slideshow. So what we want to discuss is what info can we get from this data sheet that would be helpful for our exploitation purposes for eCTF. If you guys can't access the slides, let us know.
So FYI, and this is something that I only learned about when I was looking at microcontrollers, but
Right? Like, why would you allow write permissions like across memory regions, right? Like, that's so weird.
I think
like you go back to or something, and then you forgot to like.
I forgot something.
Yeah.
actually going to the slides real quickly. I think I might be able to explain, but I don't really know.
The ghosting?
The ghosting, I'm just guessing, by the way. I don't actually know.
What's your thought?
So I think the idea is that with the ghosting, like if you had an MMU, you could say MPU, you could say like, oh, I don't want direct writes to SRAM.
Mhm.
Or I could set like this ghost region to be read only, which is very common. You'll have like a read only section of region, which is accessible to like the unprivileged, the unprivileged context.
Mm.
And then the main SRAM is like, which is readable and writable, but only by privileged
Yeah.
application. So I like the Max 70,000 had I believe ghosting, but just for like reading. But I don't really know what's going on here, actually. Yeah.
Ghosting if it's not read only, right? Like, why
Yeah.
would you?
Yeah, the thing is, like, he was discussing, like, out the memory offset, like, you can write through.
You can write to multiple memory addresses. Like every ghost, it's an auto write, which is like what?
All right. Yeah. But okay. So everyone, I'm going to go through like the user guide. So as you can see, the user guide is 1,800 pages long. Going through all 1,800 pages would be a pain. So what I like to do is go through the table of contents and see exactly what things interest me. So one of the very first things I look at is the architecture, just to understand how the system is like structured. So it's that's all. So the system block diagram is pretty useful just to see like all the peripherals and the main they'll like try to put all the features which you'll find in this document in here. So you'll see that there's actually sort of two peripheral buses here. One is for one is PD1. So you can, the peripheral buses are just like separate peripheral accesses. So like this would have its own memory region for this peripheral bus. This would have a separate memory region, and these memory regions have access to the corresponding peripherals for these. So TIM is going to be timers. You have like comparators. You have SPI peripheral ADC, which is analog digital converter. They have AES. So this is a hardware accelerated implementation of advanced encryption standard. So you can use this for really fast encryption if you wanted to do that. And then the PD0 peripheral bus is where you're going to see like our UARTs here, I2C. So and we also have our debug assets as well. One important note is that on ARM, it's not JTAG, it's software debug, SWD. So SWD is special because it only uses 2 pins. So SW clock and SWD IO. So it is able to communicate with only 2 wires as opposed to JTAG, which has 4. The other thing I like to look for is the memory map. So, you know, like back in our presentation here, like this was the memory map for the Dish Network smart card. As you can see, the smart card did not have that much memory. It literally went to a maximum of like 000 to 65,000. Is that right? 535 bytes, which is not a lot. And as opposed to looking at the memory map here, you get the full 32-bit addresses. Now, that is really big. Microcontrollers are never going to use the full space, but it's addressed that way. And so because of that, you need to know where things are in memory. So the top level memory map is really useful because it says exactly where things are located. Most commonly on ARM chips, you're going to find all the peripherals starting at like this 4th. I don't really know how to read addresses in a concise way, but like this like 4,012. I don't really that address. Okay. That's just for the 4. RAM usually also starts at 2. And then code can start at 0. It can also start at 1 sometimes. And a lot of the times you'll see ghosting properties for code regions. So sometimes, actually that might be false, but that's just from what I've seen. And then the system PPB. So what this means is this is actually the memory of region reserved for ARM microcontrollers. So if you see this E0 address, like this is defined in the ARM spec. Every ARM microcontroller or CPU will be using this memory address region, this memory region for the ARM peripherals. So again, like does anyone remember like some ARM peripherals that we might have mentioned earlier, which we might want to program here? So UART would actually not be part of the ARM peripheral bus. So it would actually be part of the microcontroller peripheral bus. So the ARM does not require it. I don't think it does, but I'm pretty sure it doesn't require you to have UART. Like you can make a microcontroller without UART and still have it be ARM compatible. So ARM has a few peripherals. One of the big ones is like SysTick. So there's a SysTick timer. This is kind of like just keeping track of how many instructions have passed since the start of the execution. Another thing is the MPU. So we discussed the MPU earlier in the slides. That's the memory protection unit. Going back to that. Or was it? Did I scroll past it? MPU. Yes. So that's the memory protection unit. So again, this is defined by ARM. So if you have a certain ARM processor and like M0, M0 will say all ARM processors need a memory protection unit. So you know you're going to have a memory protection unit. And so if I try to figure out like how do I program my MPU, if I search up Control F, MPU, I'm not going to find it. I actually only get two results. And again, that's because this is in the system PBB region, which is that E0 address. And the only way you're going to find out how to program that is if you go to the ARM documentation. So again, the data sheet, even though this user guide covers all MSP M0 chips, it doesn't go up the level of defining what ARM features are on there, because those are just assumed to be there by default. Does anyone have any questions about that front? So
What kind of stuff when you program the MPU to do?
So the MPU basically says, okay, so by default, all the memory regions on your microcontroller are going to have like read, write, and probably execute. So every region of memory you can read to, read from, write to, and execute. That's the default behavior. And so what I can do is, because memory is organized in pages, I can say like, okay, the MPU basically says that if I can program a certain page of memory to only be executable, so I can't read or write to it. And so if I had code, if I configure the MPU, so no, you have to configure it, you have to run the MPU configuration on boot. And then I have code which to program the MPU, which says, okay, 210000 to 22000 is read only. If I try to execute from that later on or write to it, it's going to cause a memory fault. So if you've ever seen if you've ever programmed a like interrupt or exception handling, you'll see like a memory fault. That's what that means. So when we're talking about embedded pwn, and let's say in the worst case scenario, somebody manages to exploit a buffer overflow in our code, and now they can write some shell code into memory and then execute it. We can stop that by saying, okay, we want SRAM, because remember, SRAM is sort of like volatile memory. It's not where our code is. Our code is at 0x00. So we don't need to execute any code in this region. So what we can do is we can say, okay, this region is read and write only, no execute. And so you would not be able to execute from SRAM, which means that if I exploit a buffer overflow and I have shellcode in SRAM now, and then I try to execute from SRAM, it's going to crash. So MPUs are great because they can prevent that type of those fully exploiting those buffer overflows.
Is it by default already protecting some of the?
So usually no. So so this is why it's kind of crucial for us to program the MPU. Although if we're using Rust, then we won't have buffer overflows. So, but it's a good idea to program it in anyways. And sometimes, actually, a lot of the times you'll have code that runs from SRAM, legitimately. So there are actually reasons for this. So one of the things is like, usually code is backed by Flash, right? So that's different from SRAM because that's like written bits that we load from. And when you can have a peripheral. So you have a peripheral here, which is actually a Flash programmer. So you basically tell the Flash programmer at this address, hey, go program Flash at this address, and it will do that. Sometimes when the Flash programmer is flashing to code, to the Flash memory, you can't execute from there because you're basically trying to execute while the Flash programmer is flashing the code. And so that can cause a lot of problems. So a lot of times you'll see code will be stored in SRAM for flashing the code region. So it'll temporarily switch this SRAM. It will temporarily start executing here, and then, or what the code will do is it'll copy the flash copying code from flash into SRAM, and then it'll start executing from SRAM. That code then starts flashing here, and then returns. So that was a little bit of a long, convoluted process, but that is one reason why we might want to execute from SRAM. And in that case, because we have executable code, right, we have this dilemma where we now want to write code to SRAM and then also execute it. So usually when you do your MPU, you want to make sure you do that after you copy your code into SRAM. So basically you have an initialization step, which sets up all this memory and the code and puts it into places. That's what we call like, what's it called? Like you write the linker script to do it, and then the linker script will automatically, the loader, I guess the loader. Sure. Oh yeah, it's literally just like a bootloader. Yeah, it loads code into the proper regions. And then you want to have the MPU protect stuff. So that's that. Okay, but I spent a lot of time on this part. There's a lot of interesting things here as well. Maybe. Yeah. So going back to the table of contents, so architecture is like probably the best thing to look at first, but then after that, like I see something that's interesting here is the security section. And one of the other things I'm also very interested in as like a hardware hacker is debug. Because if you get debug access to the hardware, you can do just like a lot more. So just for sake, like I'm going to click on debug first. Again, so the debug SS interface is for the ARM serial wire debug. So it's not software debug, sorry, it's serial wire. Okay. But that makes sense because it's over 2 wires, which is serial. Except it's not exactly like that because it's like one's a clock and one's IO, but and okay, so what I'm looking for is like basically how exactly does the chip allow you to lock down the debug port? So this kind of goes over physical things. So here, so like after a power on reset, you'll see this a lot because a power on reset is different from a lot of different types of reset. Basically, power on reset is you shut off the power to the controller and then you turn it back on. It configures the SID pins, and yeah, so if the device configuration has not permanently disabled all SID access, then the SID interface is enabled during the boot process and a debug probe can be connected. So basically, I just confirmed that there is some sort of SID lock, which most microcontrollers have nowadays. But there is some sort of device configuration. So now I'm interested in how, like, what does this device configuration mean? So, oh, yeah, and then I think this is just breaking down the actual debug information, but here, there's a restricting debug access. So there is this debug configuration, which defines like you just sort of see like there's a debug enabled with password, debug disabled, SID disabled, and so SID disabled means enabled. So just FYI. And here there's like a 128-bit plain text password. So presumably you'd have to send like look, this is like telling you exactly how you would add a password and then also authenticate with that. So look at this, like what is PWD factory reset? Okay, so I guess factory reset is like you can set a password for what the factory reset password is, maybe. There's a lot of interesting stuff here. There's actually, it's a lot. Like there's a factory reset and master race. Okay. Yeah, but this is something interesting. So you guys can take a look at that as well. And then security is also an important section to check. So we do have true random number generation, which is like very good. We don't have to try to find entropy from random sources, although we still want to do this because as you'll learn, if you have something random and you combine it with something not random, it's still random. So that means as long as you pull as many random sources as you can, as long as one of them is random, your output's going to be random. So, and we'll talk a little bit more about that when we do more programming stuff.
How does it generate like true random?
So it's a black box. You don't know. They probably do, maybe Texas Instruments documents it somewhere, but for the most part, for a lot of these, for a lot of microcontroller manufacturers, they don't tell you exactly how they get their entropy, because otherwise then you might be able to reverse and figure it out. But presumably it's like looking at like inherently the only thing that's going into a microcontroller is a bunch of analog electrical signals. So it's probably just looking for some variation and creating randomness from that. And one thing it probably also does is it has an internal state where it keeps track of some like seed, which is constantly updating. So that way, even if you manipulate the electrical pulses, like there's still some randomness from that seed it's kept track of.
They actually go into a little bit of detail about how it works.
Do they?
Yeah.
So like if you go into TRNG here,
Let's
see.
I mean, it's not like an incredible amount of detail, but it gives you an idea of what's going on.
Yeah, so you can see there's an analog block. Entropy source. aptly named. And yeah, you can see like here, like this is how it has some logic where it is yeah, getting the values from the entropy. There's a health test. Like this is actually really crucial, right? Because like let's say I manipulated the entropy source to always be zeros. Like let's say I figure out an attack to do that. Because that could be something feasible. Like I could shine a light, like a ray or something, and then it's always like powered. So it's always ones. So a health test is important because it will like check like, oh, is my entropy source actually feeding me like random things? And so what those it'll sample a bunch of that. There's some formulas that you can run, which will check the entropy of that data, and then it will use that to initialize its state. But yeah, this is cool. This is something that we can also look into as well. But to be honest, trying to break TRNG for Texas Instruments is probably going to be insane. So
But if it happens, they'll give us $1 billion.
probably $1 billion, yeah.
Oh, wow, they actually go into a fair amount of detail about the health checks too. There's actually a little more detail.
Health checks,
No, there's like much more detail.
so like analog. Yeah, so like if functions checks if it's functioning properly by capturing 4,096 consecutive analog samples and verify that it passes a health test. Yeah, so if the test has failed, this indicates there's a severe loss of entropy, and then it can't be used, so it will I guess blow up. It'll trigger a RQ health fail interrupt, power off. Okay, so it just keeps looping, and then it blows up. So a 3 time after the 3rd time it'll blow up. I guess.
Yeah, there's runtime tests as well.
Yeah. Like this is really good. This is really good. Actually, I've never seen so much documentation about the TRNG. Like usually it's like it still is a black box because they're not going to give you the Verilog or anything. But
That is good.
yeah. Mhm. But yeah, so back to sort of security section. So actually, one of the most important things that we'll eventually talk about in a future presentation, probably firmware security, is secure bootloaders and secure boot. So the idea is that we don't want somebody to be able to load custom code onto a device that we put out into production. Because for the same reasons that we mentioned here, right? Like if we were able to write some code, then we can leak out the rest of the original code. And so for that reason, we don't like the top priority is to prevent somebody from running their own code on our system. So secure boot prevents that. Basically, if it sees that some memory has been written, if it doesn't fail like some sort of integrity check, then it's going to stop the boot process. And so like you can see there's this concept of customer secure code, which is like some firmware that you write as the manufacturer to enable customers to do like updates. Because firmware updates inherently involve writing new code to the device. So if you're trying to prevent people from writing their own code onto the device, but you want to be able to provide firmware updates, you need to provide your own firmware code in order to facilitate that process. So the customer secure code is what does that. And in order to facilitate that, Texas Instruments will come, the controller will come with its own bootloader. And so that bootloader will do things like actually adding in the secure code and things like that. So this flow chart here is usually what you're trying to look for. So on a system reset, you're going to check if there's a customer secure code. And if it does exist, then you're going to jump into basically a stage 2 bootloader. So if you guys remember the first presentation that we had like stage 1, stage 2 bootloader. So like this is the stage 1 bootloader. This is the very first thing that happens when you turn on the device. And so if there is no stage 2 bootloader, it just jumps to the main application. It just runs the code that's on the device. We expect for eCTF that MITRE will have their own secure bootloader, which will be placed here, right? So that secure bootloader will be able to run its own code to allow you to program the device. And there's like a setup process, and if you pass like the boot checks, then you go into the main application.
So like what kind of if secure boot wasn't like didn't exist, what kind of exploits can you like do? So
secure boot didn't exist, then you could just overwrite code, like you can write your own code to the device and then you can control the device. So that includes like writing part of your code into the device and then dumping out the rest of the code. So dumping out somebody else's code doesn't sound super useful, but realize that like most secrets, like if I have like secret keys or something, like they'll be encoded in the binary. So by reading out code, I can get those secrets.
Is there any way to like stop it from happening with the NPU or?
So well, at that point, like you've compromised basically the execution process. Like, so like if I'm able to program like my own application into main application, right? It doesn't matter because like this boot code is not going to initialize the NPU for me.
Yeah.
So I can overwrite part of that. I can run my own code and then there's no NPU at that point.
Yeah.
So here in this CSC, you probably have that code to set up the NPU. You'd have that code to lock things down as much as you can, like turn off SD software debug. Although it's probably going to be permanently disabled.
What is CSC?
So that's the customer secure code.
Oh.
So they call this customer secure code because they mean like from the Texas Instruments perspective, the customer is like Miter in this case.
Yeah.
And so Miter is a customer, but they also want us to be able to run our code. So they're going to write their own bootloader to allow us to run our code. Yeah, and they even give like code, like C code straight up to just like for programming it, which is like wild. I would never expect to see code in my user guide.
That's cool.
With analog devices. Yeah, and then they even have things like flash memory protection. So I mean, this is pretty much a given, but like they have flash banks. So basically what that means is you can have two blocks of flash which are the same size, and you can switch between which flash bank is being used to execute. So like this is good for like firmware updates. So like if I was executing from flashbank 1 and then I'm doing a firmware upgrade, I want to upgrade to the bank that I'm not using. So in case the upgrade fails, I still have code I can recover to. And there's write protection. There's read execute protection. There's a lot of different protections here. There's SRAM protection even. Is this separate from the MPU? I don't know. But I suppose it is because it's under the system control register. Yeah, so there's a lot of interesting things here. And these are things that we want to consider when we're programming our device. Yeah. Does anyone have any questions? I kind of like went on a rant. I won't give the microphone to someone else, so I don't lost this one.
This is a little interesting. There's just a single address.
Oh, entire SRAM. Oh, you say like any address
Address this break, like it's RWX and before it's IW. This enforces right XOR, so you can't.
Wait, shouldn't it be
No, sorry, sign up to
updated?
RWX, RX or RW.
You want your writable memory to be after your code, because if it's before your code, then you can write into it.
Yeah, it's just interesting. It's not like page level or something. It's just
Yeah, no, like
our one
it's
address.
wait, hold on. So what was this command? It was SRAM protection. There is which register would this be? Sex status?
Yeah, sys control.
Oh no, it's in syscontrol. Oh right, hold on. I have to go. So now like you'll see the syntax where it's like syscontrol.soclock.sram boundary. So this is the peripheral. This is the wait, what the fuck is that? This is a register. What is in between that?
Just like
It's the
bit of the.
Oh no, this is the register. This is the field, I believe. So peripheral register field. So if we find sysctl peripheral somewhere, it might be just in syscp. Okay, I'm just going for F. SO clock 1178. Thank you.
No, sorry, that's like the address. Sorry.
The address? Wait,
Sorry, the page is 214.
214. Okay, thank you. All right.
The is
Oh, is it like
1178, which is the offset.
oh, but it doesn't say oh go okay there. So here you put the address in there and any non-zero value can be configured. Yeah, so it's just it's not page level. It's not like a page offset, it's just straight up.
Address, yeah.
Yeah, okay, that's interesting. Well, we should use the NPU and we should use this.
They conflict.
I don't know. That'd be interesting test.
Like,
Like that might be a security assumption in which I assume they've tested it, but that could be, you know, bad security assumption for
it's weird, right? Because NPU doesn't work like that, right?
it doesn't.
Yeah.
It's page level.
Yeah.
Wait, what is the order, like, when is that, like, in the boot order can,
Oh, so like this like
address
address.
versus the NPU, like, does it happen at the same time, or?
It doesn't matter. Like one can happen before the other.
Okay,
That's like based on the, like we can write code to do that. The CSC can write code to do that. They can do it in different orders. Like,
Wait, what
yeah.
are you asking? Like when you configure it or when it's used?
I guess, like, what is the, if both of these are like protecting,
Like the same region of memory.
Yeah,
Like
like
which
some-
would you do first?
Yeah, I guess that's what I was asking, if it's not clear which would take precedence.
Yeah.
Like,
Yeah.
if it's like the least permissions that are configured by either method.
Or the most, yeah.
Right.
Yeah, I don't know.
this is like, which device is this part of?
It's-
This is the S.
It's
right?
part of the controller.
Okay.
It's like a system register for the controller. So this is Texas Instruments' own thing, separate from ARM.
And yeah, this prevents buffer overflow, just because it specifically says here, we didn't say before, that you can't write to X rate, which I guess makes sense.
How are they keeping you from writing? How would you normally do it? How would they? Do you have physical access?
So
Try writing it.
normally normally the way you program program a microcontroller when you're developing is you're going to write to the debug port.
Sure.
So you're going to use SID. If SID is disabled, then the only way you can write to flash is with the flash controller peripheral. And the only way you can control that peripheral is if you have code on the existing device to program that peripheral.
Oh.
So that's where we have like the bootloaders,
Oh.
right? So in that case, like the only way to program your own code is to interact with the defined bootloader.
Or defined.
Yeah.
This function is defined by the specification.
Yeah. So yeah, that's why. You can't just write your own code.
Theoretically, you could.
Yeah, so a lot of times, like when you have like an SID permanent lock or like even like a temporary lock, when you're going, sometimes they'll let you like revert back to an unlocked state, but when you do that, it permanently erases everything. So it does a mass erase. There's actually a text related to this where this was documented in Travis Goodspeed's microcontroller exploits, where they unlock they send the command to unlock the software debug. So that's initiates a mass erase, but then they shut off the controller before the mass erase happens. And when they turn it back on, SID is enabled and you can see all the memory. So you would put the SID enable at the end of the mass erase. So you want to make sure you mass erase. And then, yeah, so like, again, there's like different attacks here too. And that's in like the Texas Instruments bootloader code, or like that would be in the chip bootloader code.
Yeah.
Like there could be bugs in the user bootloader code, which would be like minor, but we're not allowed to attack that. So you'll see in the ECTF, they're like, you're not allowed to attack the minor secure bootloader, which is like a clear, like a definition, which I literally take as, okay, that means we can attack the Texas Instruments bootloader.
Much less secure.
But yeah, that's all. Do you guys have any closing statements? Can you just pull the slides back up? Yeah. I just have this, but
I think, yeah, honestly, it was just, we just wanted to go over, how you can read different manuals, data sheets, things like that, because that's gonna be very important for next semester when we do ECTF. And then just announcements wise, our next meeting is next Monday and it'll be attacking, not actually secure protocols, secure protocols.
yeah.
Yeah.
Yeah.